You've already learned that the three measures of center in statistics are mean, median, and mode. I also shared with you that we don't tend to really use mode too often. So therefore, we're kind of going to focus on mean and median, specifically in this lesson, in terms of when is the best time to use one or the other. Because if you think about it, that's a really key question in this whole topic. If there's two measures of center, which one's better to use and when is it better to use it? Okay, let's look at an example to better explain this concept. Just for argument's sake, let's suppose we have a statistics class with 20 students, and I ask for their ages. So this table of raw data, which happens to be ordered very nicely, is basically the ages of students in a statistics class. I have also provided the mean and the median age of those students. The first observation to be made here is there is an age that isn't like the other ones. That is the 65 years old. So we refer to this particular observation as an extreme observation. An extreme observation is basically any observation that falls outside the realm of the other data points. It doesn't look like it belongs in a sense in terms of the number. What's interesting about extreme observations is they tend to have an effect on certain measures of center. So I'm just going to show you with a visual example here on which one it does have an effect on. You might have an idea of already. So if you were to take these two numbers, 23.8 and 21.5, which one of them actually seems to better describe the actual center of this data set? If you look closely, you're going to see that our mean, 23.8, would fall somewhere in this realm right here, which means that it would only have 3 observations that are higher than it, which means that it would have 17 that are lower than it. So that means that doesn't seem like a very good measure of center for us to use. But if you look at the median falls about right here. If you count out, it looks like there's about 10 below and 10 above, which is a pretty good measure of center. So therefore, in this data set, I would probably use the median in order to describe the measure of center. Now, it turns out that generally, whenever there are extreme observations present in your data set, that the median is the preferred measure of center. But why is that? Because the median takes the middlemost data entry no matter what. It doesn't care mathematically what is going on the ends of the data set. So whether this was a 65 or a 25, it doesn't care. It's still going to go to the center of the data set. But the mean, that's a whole different story. The mean is using each value in the computation of that measure, that statistic. So therefore, it's going to be pulled towards the extreme observation, which it was, by the way. It ended up here, which is going to make it a poor judge of the center of the distribution. So you might think, or any student might think, well, why do we use the mean anyway? Like, why can't we just use the median all the time? Because there is something to the fact that you're using every data point in the mean calculation. That's actually really nice and more accurate in terms of finding a center, but it just doesn't work well when there's an extreme observation. It's almost like an extreme observation is its kryptonite, is the best way to put it. Okay, so it turns out that there's an important term that we use in this concept, and it's the term resistant. So we say that a measure is resistant if it is not sensitive to extreme observations. Okay, so what does that mean? If we're going in terms of our example, which one of these measures was the one that wasn't sensitive to the extreme observations. In other words, it wasn't affected by it. It was the median. So therefore, we would say that the median is resistant. Whereas the mean was sensitive to extreme observation, so we would say the mean is non-resistant. Okay, we are going to be using these terms more as we go forward because it's going to have the same effect on some of our other measures that are introduced. But for now, you want to keep in mind that the mean is going to be basically annihilated by extreme observations, and the median, in a sense, almost has a shield up and saying, well, you can't really hurt me because I'm going to the middle no matter what. This concept also has a very interesting application in the world of distribution shapes. So how does resistance relate to shape? That's what we want to concentrate on. So let's talk about our three main shapes. So we got symmetric, right? So that looks like this guy. So when we look at a symmetric distribution, that's a terrible symmetric distribution. Try that again. Okay. We're basically looking at something that is exactly what it sounds like. It's symmetric. It's the same on both sides. We don't expect any extreme observations, anything from that genre of observation. So therefore, we would expect that the median is in the middle no matter what, but then we would also say that the mean also is located here as well. Because if it's symmetric on both sides, think about that mathematically. Everything on the left is going to pretty much equal everything on this other side, and it's all going to level out, and you're going to get a mean and a median that are basically going to be the same. So mean equals median. Okay, let's look at yet another shape. Let's say we have a left skewed distribution. Okay, what does that look like? That would be something like this, right? We would expect the median to be similar location towards the center of the distribution, but we now do have extreme observations likely in a left skewed distribution. As a matter of fact, they're almost certainly going to be in our left tail because they're far away from the actual main part of the data set, which means if you think about it, what is a really small extreme observation going to do to the mean? It's going to make the mean less in value. And we know that this bottom piece right here is just a number line going across, right? So that means we're looking for the mean to be pulled in this direction. Therefore, that would be someplace over there. So it turns out that the mean happens to be less than the median in left skewed distributions. Looking at our last shape, right skewed. So that's going to look something like this, right? So again, the median is going to be towards the center of the distribution or near the arc, but a little bit in a bit. But our extreme observations are going to be located this time in the right tail. So what is that going to do to the mean? It's going to pull it towards it. So again, it's going to pull this way because now we have higher values being put in the mean formula to make the number larger. So that means the mean is going to be somewhat this way. So in other words, whenever you have a right skew distribution, then the mean is always going to be greater than the median. So the interesting application of this is simple. If you're given two values, let's say a mean and a median of a data set, the value they have with respect to each other can tell you the shape of the distribution. So if I have a mean and the median that are both the same, then I'm going to assume that my distribution is symmetric. But if I have a mean that is less than a median, I'm going to assume it's left skewed. And a mean greater than the median means right skewed. So just remember this example up here? So this is a mean that's greater than the median. So if we go back, which one of these scenarios, 1, 2, or 3, was that the mean was greater than the median? It was this one. So we would expect if we graphed this distribution that we would have a right skewed distribution.